Assalamu alaikum everyone, I hope you're doing good. So in today's simulation we are trying to produce hydrogen from glycerol stream reforming in a supercritical water with the CO2 absorption unit. However, in this simulation I'm not going to do a CO2 absorption process. I'm only trying to cover the production of hydrogen from glycerol by using a stream reforming process. So the information for this simulation has been taken from this publication, which you can find online. So all the information regarding the parameters, the conditions, the operating conditions, the working condition, directions has been taken from this publication. So let me read out some of the information and then we can jump on straight to the simulation. So glycerol is expected to be an adequate renewable resource for hydrogen production in the future because it is a byproduct of biodiesel production. In this work, the crude glycerol contains 88% of glycerol and 28% of methanol is used to perform a thermodynamic analysis of hydrogen production via glycerol supercritical stream reforming process. Using a Gibbs-free energy minimization process in Aspen Plus. The effect of operating condition, for example, the temperature, the pressure, the ratio of the supercritical water to crude glycerol ratio in the reformer were analyzed. The simulation result shows that the suitable operating conditions for the reformer, giving a 65% of hydrogen in the gas products, are temperature, pressure, and the ratio of glycerol to water, which is about 800 degrees Celsius to 48 atmospheric for the pressure and 90 for the ratio. However, the purity of hydrogen is still not suitable for industry application. Therefore, the hydrogen purification process, including the gas liquid separation unit and CO2 absorption process using monoethylamine, is used in absorption media, whereas in this simulation I'm not going to touch the absorption process. The only process that we are going to simulate here is production of hydrogen, and then we can try looking at how we can vary the temperature and see the effect on the composition of the product. So what we are trying to cover here is a kind of flow sheet which is shown here, where you have a supercritical water and glycerol is mixed with the mixer, and then we can compressed heat and then send to the reactor, and then after the reactor then we can send it, we can lower down the pressure and then we can cool down and then send to the to another reactor, and this is the equilibrium reactor, and the reactor that we are using here is Gibbs reactor. And after it is being after the reaction in the equilibrium reactor, then we can use the top product and cool it down, and then you can separate in a separator. And there are some information which is mentioned here, the operating condition which is mentioned. So for the compressor we have 200 to 300 atmospheric, for the heater 500 to 1000 degrees Celsius, for the reactor we are using 500 and 240 atmospheric, and then we can vary this and we can see this how we can what is the effect of changing the temperature and the pressure on the product. And then we can have a turbine pressure, the cooler, however here it is mentioned 200 degrees Celsius, but I think it is wrong, because the temperature for the cooler is 20 degrees Celsius. So by typographical mistake, this one is supposed to be 20 degrees Celsius. And then in the reactor we have 200 degrees Celsius and 1.4 atmospheric. In the cooler 2 we have a temperature of 60 degrees Celsius, and in the separator we have a pressure of 1.4 atmospheric and 60 degrees Celsius. So without any further ado, let's jump into the simulation and let's see what we are trying to achieve today. So we can start with the new simulation, and I will just pull this one a little bit below so I can see the components that we are using. So I'm going to take assistance of the reaction that we have. So we have this component that is present. So let me add one by one. So the first one is glycerol, which is C3H8O3. I can call this one GLY. The second component is water. Third one is carbon dioxide. Fourth is hydrogen. Then we have carbon monoxide. And what else we have? We need methanol. Then we have methane. I think that's all. So we have 1, 2, 3, 4, 5, 6, 7 components that is added. So according to this paper, they use NRTL equation of state. So we choose NRTL equation of state for the simulation, and then we can click on the next option, and here we need to make sure that we need to click on estimate using the parameters for unific is being calculated, and we need to check this mark, which is estimate using unific. The parameters should be calculated by using this process. Okay, so let me just click next. You can start run the process, and all the parameters has been estimated, and then we can move on to the simulation environment. Let me pull this one on this side and this one on the other side, so I can see both screens clearly. So let's start with the first part, which is adding the two feed streams. So we can add a mixer, and the mixer we can add two inlet streams, one for the glycerol and one for the supercritical water. So I can call this one W1, and the second one I can call it glycerol. Right, and then we can have an output. The output stream we can call it F1, and this one I can simply say it is called mix stream. Right, so let me go into the glycerol composition part, and according to the information mentioned in the paper, glycerol composition is 80% of glycerol and 20% of methanol. So, and the conditions for the temperature pressure conditions are 25 degrees Celsius, and the 25 degrees Celsius. The pressure is 1 atmospheric. So change this to atmospheric. The flow rate is mentioned 100 kg/mole. So, and the composition in terms of mole fraction will be 80% of glycerol and 20% of methanol. Moving to the next inlet stream, which is for the supercritical water. The temperature for supercritical water is 500 degrees Celsius. Pressure in terms of atmospheric is 240, and then for the flow rate, which is 900. So basically what we are trying to achieve here, we are using let's say we use 100 kg/mole for glycerol, and the remaining, let's say 10% of glycerol and the remaining 90% of water is used. Then we can vary the concentration later on, and we can see how we can achieve what is the effect of changing the concentration of both water and glycerol on the product. Right, so the composition, and obviously it is pure water, so we can say the mole fraction for glycerol is pure water. Then we can click on the run option, and it will take some time, and then the results are calculated. So we can move to the result option, which is F1, and here you can see we have the mix stream information, which is shown up here, which is 90% of glycerol, obviously not 90%, but like 10% of glycerol and the remaining is water. Right, this is a mixed stream. So let's move on to the next part of the simulation, which is to add a compressor. So here we have a compressor. So to add a compressor, just click on the pressure changes and then add the compressor, connect them together, align them, and then we have the outlet from the compressor. Okay, we can align them. This one is called compress, and that one is called F2. Right, so the compressor that we have is working at a pressure about 200 atmospheric pressure. If you click on the compressor, the option that we need to use is isentropic, and the discharge pressure in this case is 200. Before we can start the run, we can just make sure that the convergence has to be vapor and liquid. In this way we can get both phases will be mentioned in the compressor. Otherwise there will be an error in the compressor. So we can just show the results, and the results you can see we already compress it to 200 atmospheric, whereas in this condition is shown in bar. Okay, let's move on to the next part, which is how to use a heater. So we can click on the exchanger and add a heater here. So double tap and join these streams together. Right, so we just do some tidy work. This one is called heater or heat, and the outlet of the heater is called F3. Right, so just we need to know what is the pressure here. So we have 200 bar, so that is 200 bar. The temperature for the heater is 500 degrees Celsius initially. We can vary this one later on to see the effect of changing the temperature on the product. So we can just click on the run option and it is converge straight away. Okay, let's move on to the next part, which is to add a reactor, the Gibbs reactor. So to add a Gibbs reactor, we can click on the reactor and we can click on the Gibbs I think is Gibbs reactor, yes. Click on the reactor and add it in front of the stream. So double tap, align the stream, and we can not double tap, just we need to add outlet stream. Right, so we can call this reactor SW reformer, and the outlet stream we can call it as P1. Right, the reactor is operating at a temperature about 500 degrees Celsius, 500 degrees Celsius with a pressure about 240 atmospheric. Change this to atmospheric, 240 atmospheric. Right, so after this we click on run, and we are expecting to get some products here. Result. So if you click on the mole fraction, you can see we have some product. Based on the equilibrium information, we get some separation. We can see we have hydrogen, carbon dioxide, water, glycerol, methanol, and methane. By looking at this information, we can see methane is being calculated in very high amount, about 50% of methane. Then we have carbon dioxide, we have a small amount of hydrogen as well. So let's move on to the next part, which is by adding a turbine. So to add a turbine, again we can click on the compressor and add a turbine in front of the streams. We can align them, give the output from a turbine. We can call this turbine, and the outlet of the turbine is being called as P2. Right, we can make it a line as well. Let me join this again. Right, P2. Right, so according to the information, this is also isentropic. The discharge pressure from the turbine is 1.4 atmospheric. 1.4 atmospheric. Click run, and we are supposed to get the pressure reduction 1.4 atmospheric. Right. Moving on to the next part. Now we need to add a cooler. To add a cooler, we need to click on the exchanger and add a heater, and then we can use heater as a cooler. So double tap and connect the streams and the outlet stream. We can call this one cooler 1, and the outlet from the cooler is called P3. We can check the information of pressure here because we need to use this pressure in the cooler. Double tap, use the same pressure which is entering, and for temperature, for cooler we need to use 20 degrees Celsius, not 200 degrees Celsius. Then we can click on run. We are getting some error in the turbine, so we will make sure that the convergence has to be vapor liquid. Now we are getting the right result, which is 20 degrees Celsius. It's cooled down. Okay. After the cooling process, we can send this one to equilibrium reactor. So we can select the equilibrium reactor, click and add a equilibrium reactor. Since equilibrium reactor requires a reactions, so we need to add all the reactions that is participating in this reactor. Right, we have two outlets, one from the top, one from the bottom. The reactor is called W shift, water gas shift reaction, and the top product is called P4. The bottom product is called W3. You can align it properly. Right, so this reactor is operating at 200 degrees Celsius and 1.4 atmospheric, so we make sure we need to key in the right information. 1.4 atmospheric, it is atmospheric, and the reaction that we need to add is mentioned here. The first one is glycerol reforming. So glycerol is reacting with water to produce carbon dioxide and hydrogen. One part of this is reacting with 3 parts of this to produce 3 parts of carbon dioxide and 7 parts of hydrogen. Keep everything as it is. Add a new reaction. In the reaction we have glycerol that is decomposing to produce carbon monoxide and hydrogen. This one part of this, selecting 3 parts of this and 4 parts of hydrogen. Keep everything same. Add the third reaction, which is methanol, that is reacting with water to produce carbon dioxide and hydrogen. We can call this one part of this, 1 part of this, producing 1 part of this and 3 parts of hydrogen. This is methanol reforming. Then we can add methanol decomposition, which is methanol is decomposing to produce carbon monoxide and hydrogen. Coefficients are 1 and 2, and keep everything as it is. We add now we have a reverse water gas shift reaction, which is carbon dioxide is reacting with hydrogen to produce carbon monoxide and water. Stoichiometry will be 1 and 1. Then the sixth reaction is methanation, production of methane. Carbon monoxide is reacting with hydrogen to produce methane and water. So the coefficients are 1, 3, 1 and 1. And the last one is water gas shift reaction, carbon monoxide reacting with water to produce carbon dioxide and hydrogen. 1, 1 and 1. So these are our reactions. Click on the run option. So everything is completed. Now we can check our product result, or we can just click on the water gas shift stream analysis. You can see here we have a mole fraction. Water you can see producing in both streams, top and bottom. And what else we have? We have W3. Let me click on W3. Right. P3. Okay. Why we don't have anything here? Okay, so we have some separation here. We can see. Let's move on to the next stage. Since we are operating at this much temperature, so we are not expecting anything to go to W3. Everything will go to W4. Right. So we have another cooler. We can add a cooler by using a heater. Double tap and add. Let me add this one again. Right, this one is P4. This one is called cooler 2, and the product that is coming out product. So I need to add it again. Yeah, this one is called P5, and the conditions that is used in the cooler has to have the same pressure. So we're using the same pressure which is entering, and the temperature for a cooler 2 is 60 degrees Celsius. Click next. Everything will be fine. Some warning signs are here. The last one we need to add is the separator, which is clicking on the separator, and the basic flash 2 separator is used. Double tap and add this separator, and then we can have some output from the separator, which is top and bottom. You can call the top one is SG1, it's the gas, and the bottom one we can call it W. W2, right, and the separator is operating at a condition of 60 degrees Celsius, just the same as it is entering, and 1.4 atmospheric. Click next, and everything will fine. Some warning signs, right. So if you click on the let me call this one a separator. Okay, and then we can click on next again. Right, so we just go to the stream analysis, and you can see we have some product. We have mole fraction. If you click on the mole fraction, you can see we have water, we have carbon dioxide, hydrogen is a small amount. We can check this one later on. We have methanol, small amount, we have a lot of methane. Okay, so let me do some analysis about this simulation. So what we can do, we can try to change the temperature of the reactor and see what is the effect of changing the temperature on the products that we are getting here on the P1. So to do this, we can use something called model analysis. So we can click on the model analysis, click on the sensitivity analysis, add a sensitivity analysis. So what we are trying to change here is we are trying to change the temperature of the block stream. This is a block, and we need to change the temperature of a block stream, which is called reactor SW reformer. And what we are trying to change here is the temperature. We can start with the if you look at this table, we can start with 500, and we can go all the way to 1000 degrees Celsius. 500, 1000 degrees Celsius. We can change, let's say 25 increments, so we have 21 points. Right, and then what we are trying to see the effect on the product. So let me add all those products that we are getting. So the first one we are supposed to get here is let's say carbon monoxide. This is the stream variable. It should be the mole fraction. It is a P1. It is carbon monoxide. Let's copy this one and paste it here. The second one is carbon dioxide. Copy this, paste here. The third one is glycerol. Sorry. Copy, paste, and this one is called hydrogen. Paste, and this one is called methane. Copy, paste, and this one is called methanol. Paste, and this one is called water. Right. And then we can click on tabulate, and we can fill the variables, all the variables, and we can start run. After running, we can get the results. And if you click on the results, let me add a result curve. In the result curve, we have the x-axis, which is varying the temperature, and on the y-axis we are seeing the effect on the composition. And if you look at here, we can have the information on these curves. If you look at this one, the first one is carbon dioxide. It is decreasing with the temperature. Then we have a methane, which is also decreasing with increasing temperature of the reactor. We have glycerol, that is increasing with temperature. We have hydrogen, that is increasing with temperature, and we can see the hydrogen is almost about 15% increase at 1000 degrees Celsius. Similarly, methanol is also increasing. Water amount, water amounts is increasing, and then it start to decrease on 1000 degrees Celsius. So this is the sensitivity analysis for the changing the temperature and checking and its effect on the composition of the product that we are getting in the reactor, that is P1 here. So let's see what is the effect of changing the pressure on so if we can see the pressure range is 200 to 300 atmospheric. So let me do another sensitivity analysis. This is for pressure. In fact, what we can do here, we can just delete this, and I will copy the same. Can I do this? Copy and paste. So this one, paste. I think we cannot do this. Copy and paste. So let me add another one, which is new. So in this analysis, what we are trying to see is the effect of pressure. So again, this is a block variable, and the block variable that we are using is for the reactor, and what we are trying to see this time is pressure. Let me change this to atmospheric. Starting pressure according to this paper is 200 and going all the way to 300 atmospheric. Increments will be 10, and the effect is on the composition. So we can start with carbon monoxide. It is a stream. What we are checking is the mole fraction of P1, and that is for carbon monoxide. You can copy, paste. This is for carbon dioxide. Paste. This is for glycerol. Paste. This is for hydrogen. Paste. This is for methane. Paste. This is for methanol. Paste, and that is for water. So click on tabulate, fill all variables, click run, and we can see the result. Click on the result curve to change the pressure and seeing the effect on the components. You can see from this plot is the hydrogen is decreasing with increasing pressure. Similarly, carbon monoxide is decreasing with pressure. The glycerol is increasing with pressure. The methane amount is also increasing with pressure. The methanol is increasing with pressure, and the water amount is also increasing with pressure. So we have done some sensitivity analysis, which is the effect of temperature and then the effect of pressure. In the same way, we can also do the sensitivity analysis for crude glycerol to water ratio. Right. So you can see we can successfully able to see the effect of temperature on these on the composition. Right. So I hope you understand how we can able to produce hydrogen from glycerol from Glycerol by steam reforming, supercritical water and CO2 absorption. However, in this exercise we are not touching the absorption process, but we are able to see the effect of production of hydrogen from Glycerol steam reforming in a supercritical water conditions. Thank you very much for listening. If you have any questions, please do ask in the message box. We'll try to answer those questions. Thank you very much for listening to me. Take care and bye.